Okay, as you can see, we're going to finish up. We ran out of a little bit of time last time, so we're going to do a little bit more about convection and Doppler shift. And then we're going to talk about surface luminosity and the relationship between surface temperature and color. And it's pretty important for us because now we're going to start talking about star systems outside of our solar system. So we're a little bit late in the semester, but we're making our break out of the solar system now and out to the stars. But before we do that, I want to ask you just a show of clicks, not a show of hands, you've already done that, but a set of clicks. Go ahead and start this. And either answer is correct. Yeah, go ahead and start it. Hit the refresh key if it's. I just get a count. I understand you guys looked at the moon and what, Mars? Saturn? Okay. And Saturn is tilted, right? Slightly? Is that correct? And you can actually see the front and the back of the rings. So you can actually see it in a little bit of perspective. Yeah, okay. All right, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. This is also correct. Okay, so it looks like about 63 of you went, so that's good. All right, now the way that this works, let me just reinforce, because there's one more scheduled session at the observatory later this month. This is our first November meeting. Gosh, in a month we're going to be getting ready for finals. It's always like that. You know, you start the semester and before you know it, you're getting ready for finals. Anyways, there's one more session, and what you want to do is get your observations in at the observatory, and then you have an observation sheet, and you give that to the guys at the observatory, the guys in the UCF Astronomical Society, the ones that are running it. And then they'll get it to me, and then I'll put it in. Now, so far I've only put in October 11th, because I haven't gotten the stuff from Sunday, and I haven't gotten, of course, last night's either yet. So, but as soon as I get it, we'll put those bonus points in there. And along that same topic, as long as we're talking about points and stuff, last time I showed you how to estimate your clicking pointage, and a number of you what was that? Yeah, with the red tie. Yeah, you're doing it again. What do you that's a stretch? Frat boys, I don't know. They're always something. Anyway, I showed you last time how to kind of estimate your clicking participation pointage. And a lot of you got caught napping, I think, with clicking. You didn't hit the refresh button, and you thought you were still clicking, and you were clicking, but it didn't send in your answer. And so a lot of you are looking at, like 6 out of 24, 15 out of 24. You're missing. You're here for every lecture. You've clicked for every question, but for some reason it doesn't reflect that. All right? Now there's nothing to do about it. And you're just going to have to carry that deficit, but it'll have less and less impact on your participation pointage as we complete the semester, because you're going to be using your refresh key whenever you can, and you're not going to be missing out anymore. Also, even if you do come in at the end of November after, or beginning of December after our last class, if you come in and you're still looking at 38 out of 45, which is pretty good, but it's not, what I'm shooting for is a lot of 45s, a lot of 44s, a lot of 43s. In most semesters, that is the case. But if you're coming in at a 32 out of 45 or something a little stinkier than that, if you've been to the observatory, that will more than make up for a few points missing in your clicking grades. So keep that in mind. And if you can make it, raise your hand if you've been twice or more. See, now you guys have got some mega bucks, because you can now cover up any difficulty with clicking and any stinkiness on your best 2 out of 3. Now we already dropped, if you're here for all 3 midterms, we're going to drop the lowest one, so that gets rid of a little bit of stinkiness in your grades. If you still have a little stinky exam grade, then having been to the observatory will, de-smellify that a little bit. So that's good. All right, so remember, and we got one more observatory visit at the end of the month, so if you haven't been to it, do your best. And we have other bonus point activities, so don't worry about that. If you can't make it, you work nights and whatnot, I understand. We're going to have other stuff that you'll be doing online, to review for the final. There'll be some stuff. And usually I have a big mega review on the very last lecture of the semester for bonus pointage. So we got, if you can get to class, if you can get into web courses and do some review homework, you'll be able to get some bonus pointage and stuff. So you're not totally SOL. Now, good old ALBARAIL. I understand you guys looked at that last night. Now, this is a photo from an amateur astronomer. It's a pretty nice photo. And when you look at ALBARAIL, which is like the head of the swan or the beak of the swan in Cygnus, all the way out past the black hole, Cygnus X1, and all the way out to the end, it's a pretty bright star in the constellation Cygnus, the swan. And to the naked eye, it looks like just one star, but you guys look through the telescope, and in a telescope you can resolve two, and actually this orangey yellowish one, amber, I hear people call it, up here, this one, that's actually a double star itself, we think. So, and then this one down here, this is the other star of the double, so it's actually a double star, we think. Anyway, we can visually resolve these. Because it's close enough, we can estimate the actual distance. And these things are pretty far apart, so they have really long orbits. But we've figured out most of that stuff. Now, a couple things I want to mention to you. This is ALBARAIL A. Go ahead and just put a couple dots on your notes. And if you're on a computer, you can make your first dot orange and your second one kind of light blue. Okay, ALBARAIL A, that's this orangey one, right? It's not a red giant, it's a giant star, but it's not a red giant, it's an orange giant because that's the dominant color. Okay? And its mass, we know from measuring its orbits and stuff using Kepler's third law, it's about 5 times the mass of the sun. So 5 solar masses for ALBARAIL A. That's the main star in that binary star system. Now this one down here, ALBARAIL B, and I believe they mentioned that at the observatory, that's what we call a white dwarf. And it actually looks a little bluish. And this one is 3.3 solar masses. So it's a little bit it's bigger than our sun, but it's a little bit smaller than ALBARAIL A. All right? Now, the reason that I'm drawing your attention to this is a couple things. The mass of a star is like its DNA. It's very simple. You know, you may think of, you know, you look at those convection cells on the sun and you see all this roiling, boiling trouble. And it seems fairly complicated, and it is. It's difficult to understand. But the mass of a star, 3.3 solar masses for ALBARAIL B, 5 solar masses for ALBARAIL A, that is like its DNA. If we know that figure for a star, we pretty much know everything that's going to happen to it. You know, we can't map out convection cells, but in terms of its lifetime, its brightness over time, its luminosity over time, we can map all that stuff out. Another thing that's important is the star's color. And so I want you to emphasize the star's color, and I'm really glad they gave you guys an eyeball on ALBARAIL last night. Raise your hand if you could make out that they were different colors. Good, yeah. That's just one of the reasons that's a good star to look at, because you can actually, if you can see it in the scope, you can actually see, oh, that does look, you know, orangey, and that one looks bluish. So now, just to recap, last time we talked about Doppler shift, we talked about trains, the audible sound Doppler shift, and then we talked about electromagnetic radiation. Now, this is a Dopplergram of the SUN, and what I want to point out to you, I think I got it wrong last time. The negative number, the dark, black and dark red on the left side here, those are the negative velocities. That's considered as coming toward Earth. So that part of the sun is swinging toward the Earth. Now the light-colored side over here on the right, well, that's what we would call the right limb, L-I-M-B. The right limb of the sun, that's colored light. It's almost orangey or yellow. And that's positive. And a positive velocity means it's going away from Earth. All right, and I think I had it backwards last time. Now, the point of all this picture is that if you compare, this is one object, part of it's spinning toward you on the left, part of it's spinning away from you on the right, or moving away from you on the right and moving towards you on the left. So what that tells you is that you have a spin. So go ahead and make add a spin, kind of a curvy arrow to denote the spin. All right? And this is how we can emphasize and measure the spin rate of a star. Because just knowing the Doppler shift, being able to measure the small change in the wavelength, gives me a velocity in meters per second. All right? And once I know that, either positive or negative, I can tell if there's some spin. And there's a lot of other things that we use Doppler velocities for as leverage to figure out and analyze the things that we see in the sky. So if you're awake and you're not listening to music, then you can also look at the logic of, good, wake him up, don't fall asleep, take your earbuds out. Listen to what I'm saying, not to your... I see another earbud in there, my friend. Yeah. You want to get an A in this class? You don't want to get a C? Don't listen to that music. Gosh, it's unbelievable. So here's the logic anyways. So you scan the surface, the left, the right, the top, the bottom, as small of an area as you can. You map out your velocities, and it's coded by color here. And so number 2, you calculate the velocities and you map it out. And then number 3, you decide the sense of rotation relative to your point of view. Now, we can see this with the sun as a whole. We can also see it, as I mentioned last time, in these granules of convection on the surface of the sun. So let's talk about these for a minute. These granules, here's your pull quote from chapter 15, I believe it's 15.1. This structure of the photosphere is called granulation. And they're typically 700 to 1,000 kilometers in diameter. In other words, so pretty much the size of Texas. So each little, and there's zillions of them. It's just amazing. I mean, if you drive, like I drove out to Dallas, out to Austin, Texas this summer, and oh my goodness, when you leave Louisiana and you get into Texas, you're at like mile marker 780 or 880 or something like that. And that means the other end of the interstate, mile marker 0, is 800 miles away and you're still in Texas. So it's pretty big. Anyway, so these are like looking at weather systems on the surface of the sun, but it's weather that's generated by the convection of heat from the core through the radiation zone into the convection zone and out to the surface in the photosphere. So they're ginormous. And just to remind you, convection cells that we see here on Earth, you can see it in the kitchen when you watch a pot of water boiling. You can see it outside when you see a thunderstorm. That's a gigantic to us, but shrimpy compared to the SUN. Those are convection cells, tornadoes. They come out of thunderstorms, and even hurricanes and tropical storms have a lot of convection features. Another thing I want to emphasize to you is the thin atmosphere of the sun. It's not like asphyxiating. At a typical point in the photosphere, the pressure is less than 10% of Earth's pressure at sea level. So, and I don't, I should look it up. I should figure it out. How far above the surface of the Earth do you have to go to get to 10% of atmospheric pressure at sea level? I do know that at about, I think it's about 18,000 feet, you're at 50% pressure. So make a note. The top, and the good example of that is Mount Kilimanjaro in Africa. When you get to the top of that, you got roughly half the atmosphere above you and half the atmosphere below you. So that means that you're at about 50% air pressure. And that's why it's, you get up to that height and higher, you have to carry your own oxygen. Or you have to be an ultra in shape, aerobically in shape, cardio in shape athlete. There's guys that climb to the top of Mount Everest without oxygen. I don't know how they do it, but they do. Of course, it drastically shortens your life if you do that. But anyway, so the density in that part of the atmosphere is 1/10,000th of Earth's atmospheric density. So it's sparse. It's a sparse atmosphere, but there's an enormous amount of temperature, and there's an enormous amount of things happening. Here's another pull quote. The solar photosphere, where the density of atoms is sufficiently low, and the photons can finally escape from the sun without colliding with another ion or atom. Now, what this is in the context of the core and the radiation zone. In the radiation zone, right outside the core, all the photons of light ricochet off protons and electrons, that are out there in the outer layers of the sun. And for that reason, they're constantly changing direction. They don't get very far. Eventually, they will make it to the surface, but it takes thousands of Earth years to get out to the surface. So, but eventually the density is low enough that they make one last collision with a proton or electron, and then they're free. They're they've escaped from the surface of the sun, and that's when they start heading towards Earth. All right, so convection. Here's another really cool image. Yeah, you can see these bright spots. Look at those bright spots. They're gigantic. Betelgeuse is a red supergiant, and we can see, you can make out, it's not very sharp, not like our pictures of the SUN, but we can see convection cells on the surface of Betelgeuse. So it's kind of cool. And this is a false color, if I recall correctly, this is a false color infrared image of Betelgeuse. Betelgeuse is a red supergiant. It's fairly close to us, and we can actually make out these features on the surface. It's very difficult to see surface features or any features in another star system, but we can see this one with Betelgeuse. Now, another thing I want to mention to you is that analyzing Doppler shifts helps us out in other ways, and one of the most famous is the search for exoplanets. This is a chart. Take a look at this. This is basically measuring the Doppler shift velocity, and it goes negative 50 meters per second, and it goes up to about 50 meters. I think the max is 56.04 meters per second. And this is over the period of hours and days. And they just keep remapping it. And because what they see when they look at the spectrum of 51 Pegasi, that's a fairly close star, constellation Pegasus, they can see, like H alpha getting redder, getting bluer, redder, bluer, redder, bluer, and that means it's moving away, toward. We call that a wobble. Astronomers call that a wobble. And what they've deduced from that wobble is that there's some kind of a large planet, fairly large, causing 51 Pegasi to wobble. And we can measure the wobble of our sun from Jupiter. Jupiter's big enough to cause just a little baby wobble in the orbit of the sun, or in the motion of the sun. So somebody from another star system, Alpha Centauri or Betelgeuse or any other, Polaris, if they look at the sun, they'll possibly detect something just like this, and they'll say, "Ooh, there's a fairly good sized planet there, an exoplanet." And so Jupiter is a regular planet for us, but if you're on Alpha Centauri, that would be an exoplanet. And so this is the Doppler shift. So make a note: the search for exoplanets. Doppler shift analysis gives us leverage to find exoplanets, right? And we found just bunches of them now. We've got this really nifty spacecraft up there called Kepler, and it stares at a certain part of the sky. It doesn't look, like Hubble looks at anywhere in the sky that it wants, but Kepler's just staring at one patch and just keeps re-staring at it, and it looks for small brightness variations and small Doppler shifts. And now this one was discovered. This was one of the first ones discovered, the first exoplanets discovered well before Kepler was launched. But yeah, this is 51 Pegasi. And you can see the period there, 4.231 days. So from the beginning to the end of that cycle is 4.231 days. And so every 4.231 days, they just start plotting again on the left, and just, and that's why you have all those dots. Notice also on this diagram E equals 0.014. Eccentricity. You can even figure out eccentricity, but you got to do a lot of trig and stuff like that. But yeah, you can get an eccentricity for the orbit of this planet. That's a fairly small eccentricity, but we can measure that as well. It's kind of cool. All right, so the Doppler shift idea, you know, it can catch you speeding if you're not careful, but it can also measure tons of really cool features about stars and planets and even exoplanets. Now I want to talk about surface temperature. So we're dipping backward into chapter 5, section 2 for this part of the lecture today. And this guy, Max Planck, he's the one that gave us all the tools and explanations that we needed to understand the stuff that we're about to talk about. Now, make a note, figure 3 in chapter 5.2 is extremely important, and we're going to analyze it. This is a small version of it, and I'll give you a blown up version of it in a second, but just make a note, 5.2, figure 3, that's what we call a spectrum over many wavelengths, and we're going to relate that that we measure for stars and stuff to everyday experiences. Now, surface temperature. If you have a stove at home that's electric, one of the things you know, if you're making tea, you're boiling some tea water, you turn it up to high. If you're making rice, you turn it up to high till the water boils, you add the rice in, let it get back to a boil, and then turn it all the way down to low so it simmers for 40 minutes or what have you, unless you got instant rice. But if you have regular brown rice, that's what you got to do. So when you're at home and you're in your kitchen, you know that when that burner element gets red hot, it's because of the temperature of it, right? And if you have it down to low, it just looks like a piece of grayish, blackish metal, right? But if you put your hand on it, I don't recommend that, or if you put your hand over it, you'll know that it's still warm. But even though it doesn't have any color, it hasn't gotten any visible color. But if it gets hotter and hotter, you know, as the heat goes up, yeah, it'll turn kind of a dull red and then a bright red. So toasters and hair dryers are similar. You know, when a toaster's toasting, you can look in there and you can see the little spiral wires emitting a lot of red light. And with that, they're emitting a lot of heat as well. Now, when the stove element gets white hot, well, hopefully that doesn't happen because that would be really dangerous. It's even hotter than red hot, all right? And because it's hotter, it'll boil water faster. So if it takes 5 minutes to boil water for tea, when it's red hot, it might take 2 minutes or less if it's white hot. Now, I don't think anybody here has a stove where the heating element, that little spiral thing, gets white hot. But I mean, theoretically, you could do it if it doesn't melt. Now, stars and other large objects are similar to that. And so when we're talking about analyzing the surface color and the surface temperature, just think back to your kitchen. You know, everything that we talk about with stars is more elaborate, but it's similar to what you can see every day in your kitchen. All right, and so that's why when you're in the kitchen and you're making coffee so that you can stay awake in the first class of the day, you know, you're doing good, and you're ready to think about what stars are doing. And that's really what we want to know about. Now, jot down this vocabulary term, Wien's Law, W-I-E-N, Professor Wien. It associates a color of an object, its main color, with a temperature, if it's an incandescent object. Now, this doesn't apply to like those specialized tubes of pure helium and hydrogen and neon that we looked at. Those aren't incandescent sources. But an incandescent source, like a regular incandescent light bulb, the color of it is determined by its temperature. The other thing is something called Stefan-Boltzmann. And go ahead and jot that term down. I'm going to give you an entire series of slides about both of these, A and B. Stefan-Boltzmann Law tells you how many watts per square meter are burning off your surface at a certain temperature. All right, so if you look at an object, a star, or a rock that you're heating up in a furnace, or anything else, you get the peak color, the most intense color, that'll tell you the temperature. And the Stefan-Boltzmann's law will tell you the amount of energy, and basically the luminosity of the object. So these are two really important laws. So let's first start talking about Wien's law. Okay, so here's our close-up. This is figure 3, I think it was, right? And a couple things about this I want to point out. If you can draw this, you can't draw in colors, but you can draw this kind of weird, it's a little bit shifted to the left. The peaks get sharper as the peak gets taller. And these are, what do we got here? 6,000, 5,000. These are 4 different temperatures in the Kelvin scale. So what this graph shows you is which wavelength has the most intensity, or the biggest number of photons per second. Right? That's the vertical scale, the intensity. So for the top curve, 6,000 Kelvin, the peak is up here, right up here, right? Then for 5,000, it's shifted. It's not as sharp. It's a little bit rounder, and it's shifted a little bit to the right. Now, here's the full graph again. So try to make a graph of this. So big, fairly sharp here, and label it 6,000. Not quite as sharp and slightly to the right, and label that 5,000. That's this second curve. And then fairly broad, 4,000 Kelvin. All right, go ahead and that one, the peak is outside. Here it is. The peak for 4,000 Kelvin surface temperature is outside of Roy G. Biv. I like this diagram. This is also from your textbook. It has the Roy G. Biv wavelengths shaded in as a rainbow, right? But now at 4,000 Kelvin, you've cooled down, and now your object is, the peak color of your object's in the infrared. See how it says that it divides up the wavelength range? So 0, 1,000, 2,000, and 3,000 on the horizontal scale. Those are the wavelengths in nanometers. And hey, you guys, make a side note. I should have put it in here, but I didn't. The wavelength range for visible light, Roy G. Biv, is from 400 nanometers violet to 700 nanometers red. Let me repeat that. The wavelength range for visible light, 400 nanometers for violet, for the V part of Roy G. Biv, and 700, a longer wavelength, for the R, the red end of Roy G. Biv. Okay, so 400 to 700 nanometers. And that's down here. You can see it down here. And it looks like they're a little bit deeper. They're about 300 something for violet here. But the edge of the red here is at 700, so that's about right. And it's not like a hard and fast rule that 400 is violet and 400 and 399 is ultraviolet. You might be able to see a little bit deeper into the violets, so you might be able to see 399 and 398. Somebody else might only be able, depending on their eye, they might only be able to see down to about 401. But usually the Roy G. Biv is 400 to 700 nanometers. Now, other animals, they say bees can see in infrared. I don't know of any animals that can see in ultraviolet, so below 400. But above 700, I think several animals can see a little bit into the infrared. Now, here's the last curve. The 3,000 Kelvin curve is lower than all of them. So they all kind of nest together. The peak gets broader as you decrease the temperature, and the peak shifts to the left. The peak shifts to the right as you get cooler. All right, so this is the peak down here for 3,000 Kelvin. So the maximum intensity wavelength depends on the temperature. So what this means, you can add this in your notes. The peak color, or the peak color for 6,000 kelvins is kind of yellowy green. Right? That's what that picture tells you. This is a fairly good diagram. Right? So the peak color for 6,000 kelvins is yellowy green. All right, right at the top there. Right up here. All right, now the peak color for 5,000 is red. All right. The peak color for 4,000 Kelvin, a little cooler. Another 1,000 Kelvin cooler. Definitely infrared. And also it's nested, it's down below the other two curves. And then the last one, 3,000 Kelvin, down here, it's the shortest, it's the most modest curve, and its peak is definitely in the infrared, right? So a couple things about this. First of all, the amount of energy is shown by the overall height of, for instance, 6,000 compared to 3,000. 3,000 is the power, the spectrum here is shrimpy. It's barely a blip compared to 6,000. 6,000 is sharp and nice. Now, if I put a 10,000 on this thing, it'd make 6,000 look shrimpy. All right, it's 10,000. Let me ask you a question. What would the peak color, what would you guess the peak color is for 10,000 Kelvin? No, what's your answer? I see you pointing.
Oh, I was thinking, I heard someone say like in the blue range, and I would agree.
Yeah, blue or maybe even ultraviolet, B, or somewhere in either the BIVs or maybe even in the ultraviolet. And you can calculate it. It's actually ultraviolet. It'd be about 330 nanometers, for 10,000 K. And why do I know that? Just by thinking about, just mentally calculating it, because I know this law. We're going to do a calculation with this in a second. Go ahead and write this one down. This is the Wien law, or as they call it, the Wien displacement law. The maximum wavelength is dependent on the temperature. Now, there's a numerator that's a constant. That's the displacement constant, or Wien's constant. And in metric system, it's 3 million, 3 times 10 to the 6, nanometer kelvins divided by temperature. Okay? And so basically, you just put in 3,000 and divide by whatever the temperature is in kelvins. Now, you can't use Celsius temperature, and you for darn sure can't use Fahrenheit. Right? But you use Kelvin, always a positive number, put it in the denominator and divide it into 3 million, ching, you'll have the wavelength of your maximum energy, the top of the curve, no matter what. That's his law, Wien's law. All right, now let's do a multiple choice for question number 2. Here we go. Let's see how you guys do. All right, so let's do that. There's your formula. And I changed it from 3 times 10 to the 6 into 3, 0, 0, 0, 0, 0, 0. All right, 5,000 K, surface temperature. Calculate the peak wavelength. Now, we already looked at the curve. We know it's red, but give me a number of nanometers. And, consult with your neighbor and, talk it over if you're sitting next to somebody, and if you're not sitting next to somebody, try to make friends. It's always nice to make friends. And I was talking with a student yesterday in office hours. Dr. B, how can I get a higher grade on the exams? And I told the student, find a study partner. Come to office hours with me, if you can, and find a study partner. Good. Okay, 20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3. Wait a minute. Time out. Did you hit the refresh key and type your answer in again? And it's all right. You can just type in A, B, C, or D. I forgot to tell you. All right, 20 seconds. I got to start putting that slide in my presentations. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Bing. And yeah, you guys are pretty good. The answer is 600. But if you didn't get that one right, let's go over that answer. Right here. And you know what? Everybody jot this down just for safety. Because on exam 4, if you're trying to analyze a star, you just might want to know how to do this. Right, so here's how you can start it. There's our Wiens law, 3 million nanometer Kelvin divided by temperature. So if you put a Kelvin temperature in the denominator, your answer is going to be in nanometers. So that's good. All right, so let's put 5,000 down there in the denominator. And it's kind of nice because the numerator and the denominator, the kelvins cancel out. Right now, the nanometer in the numerator doesn't cancel out, but that's all right because you want nanometers for your wavelength. A wavelength is a distance. All right? So now, the other thing that you can cancel is cancel 3 zeros, top and bottom. How about that? That's like 6th grade, but you can, it's pretty easy. All right, so then you just got to do 3,000 divided by 5. Okay, and that's 600 nanometers. And my wonderful students, 600 nanometers, that's red. That's up at the red end of Roy G. Biv. And this is how you, and that is why on this graph, can I go to the next screen? Okay, that is why for 5,000 Kelvin, the second curve down from the top, the peak is right there in the reds. Now, it's not all the way out of the reds. It's kind of in there a little bit. 600 nanometers is in there a little bit. But yeah, that's definitely red. Right? Now, side note, if I put a smaller temperature in the, so if I put a smaller temperature here, so if I put like 4,000, you can figure that wavelength. 3,000. If you put, what was the answer from last time? 37 Celsius, that's 310. If you put 310 Kelvin here, you can figure out your peak wavelength. It's in the infrared. Because body temperature is about 310, right? We figured that out last time. So 3 million divided by 310 is going to give you, so let's see. So cancel 2. That's 30,000 nanometers. Yeah. Or no, 10,000 nanometers. So that's infrared. And students, that is what the Army uses when they're making their night vision goggles, because they want to find humans on a cool background out in the desert or wherever they are in the forest. You know, not everything, you know, at the end of the day, you know, stuff cools down, but we don't cool down. We're always at 98.6. So if they tune their ultra or their infrared goggles to this wavelength with a 310 down there, yeah, they'll find a lot of humans doing that. Okay, so if you go to a cooler temperature, your peak color will be in the infrared. So make a note of that as well. Now, you're going to have some homework this weekend, and you know what I'll do? Just for safety, I'll give you a couple Wiens, or I'll give you a Wiens law displacement calculation where you actually type in a number. And you're going to answer in nanometers, or maybe to the nearest tenth of a nanometer. Okay? So get your mind ready for that. All right? Any questions before we go to the next topic? Stefan-Boltzmann. All right. The Stefan-Boltzmann law, oops, wrong direction. Here's the Stefan-Boltzmann law. Now, F is, this is straight from your textbook, chapter 5. F stands for the flux. Now, we're not talking about the flux capacitor here. We're talking about how much wattage per square meter burns off of a surface of something at temperature T. Now, so sigma is a constant of nature. And this one, there's no diagram that you can kind of figure it out like we just did with the Wien displacement law. This one there's a ton of calculus in this one, so we're not going to go over that. But yeah, every square meter of a red star, you know, like Betelgeuse, will have the same luminosity, and here it is, you know, so many joules per second per square meter. All right? Now, that is just like the solar constant. You know, we know that the solar constant, the amount of energy per second flowing to Earth from the SUN is about 1367 watts per square meter. And that's what the units of Stefan-Boltzmann law is. So the number F, or the luminosity F, is in joules per second per square meter. Now, here's the value of the constant, sigma. And so this is in watts per square meter and per Kelvin to the 4th power. And there's just a ginormous amount of calculus in this. So if I was going to ask a grad student, I wouldn't even ask an undergrad to derive this one, but maybe an undergrad, but more likely a grad student. It's a bunch of trig and calculus and all kinds of stuff in there. But the number works out 5.67 times 10 to the minus 8 watts per square meter per Kelvin to the 4th. And this applies to the surface of any star, and actually it applies to the surface of any incandescent object. The stars are particularly easy because, you know, we think of them as a sphere, and we think of them as pretty uniform temperature. Now, we saw, however, that Betelgeuse, we could make out a little bit of surface variation. And sunspots are spots that show up as dark spots because they're cooler and they're not burning off as much light as the bright area around the sunspot. But sunspots are not that much lower than 5800 Kelvin. By the way, if you want to know the peak wavelength for, that would be a good homework problem. The peak wavelength for the SUN 5800 is the temperature, surface temperature, so you can use Wiens' law to figure out the wavelength and then the color. So this applies to any star. And the nice thing about this is, if you're looking at a star, go ahead and make a note of this. You know, the fact that it applies to any star. A lot of times we can't triangulate or parallax a distance to a star. Right? But if we can see it, we can see its color. And if we can, in other words, you can put it through a spectrometer, a diffraction grating, and measure which one's brightest. Well, for the sun, it's kind of yellowy green. For Betelgeuse, it's more in the reds, cooler surface temperature. Betelgeuse is a red supergiant, so it's really bright, but not because of its temperature, just because it's a gigantic star. But you look at it, if you can see a star, even the other side of the galaxy, you might not be able to get a parallax for it, but you can measure its color, therefore its temperature. And once you get its temperature, then you know an awful lot. So let's go and review back to this part of the outline. Yeah, everyday experiences. Remember to think about stoves and, like a campfire. I remember one time up in Maine on a canoe trip, we got marooned on this island because of a big storm. We couldn't canoe off the island. But there's a lot of firewood, so we ended up being pyros, for like 2 days straight. And we built up this campfire, so it was like a furnace. We found this old iron rod on that island, from logging equipment. And we put that iron rod into our campfire and just poured on the firewood and just got that thing red hot. We started burning our names and stuff and everything like that. So, yeah, campfires, stoves and stuff. And then here are the two laws that we just talked about, Wiens' law and Stefan-Boltzmann. Now, here's the logic, all right? This diagram is the key. There's no real diagram for Stefan-Boltzmann law, F equals sigma t to the 4th. There's a lot of calculus, a lot of trig and stuff like that, but not a big diagram. But this is a pretty good diagram for the Wiens displacement law. I like this one. You see it all over the internet. Just type in Wiens' law, and you'll see jillions of pictures like this. But the one we have in the textbook is pretty good. So here's the logic. You use a diffraction grating and a light meter to measure the wavelength of the brightest color of a star. So you're looking at a star, you send the starlight through diffraction grating, and you're going to get a rainbow, a spread of colors. And a star is going to be an incandescent object, so it'll give you a rainbow of some kind. Now you might not, if you're looking at Betelgeuse or Alpha Centauri C. Alpha Centauri C is a small dwarf star. Excuse me, it's a small star. It's red. So it won't be putting out a lot of orange, yellow, green, blue, indigo, and violet. You'll see some, but most of it's going to be red and infrared for Alpha Centauri C. Same for Betelgeuse. Okay? So whatever it is, you look at your star through diffraction grating, basically. You measure you measure how many photons, you put your light cell, like the little photocell on your calculator, if you have a solar-powered calculator, Right? So you measure the strength of the light coming in, so you measure blue, and then you measure indigo, and then you measure violet, and then you measure violet, then indigo, then blue, then green, then yellow, then orange, and then red, and from that you build up your spectrum. Okay? You get that curve, and you look and see what's the top of your curve. Once you have that, then you can figure out the temperature. Right? So we use Wiens' law to get the surface temperature. So your observations using a diffraction grating and some kind of a photometer get you your curve. Okay? And then you analyze your curve. All right, okay, my peak wavelength's at about, 522 nanometers. And you put that into Wiens' displacement law, and you get a temperature. All right? And then Stefan-Boltzmann, it's just a constant sigma, which we know, and then temperature to the fourth. So once you get the temperature from your diffraction grating and from Wiens' displacement law, then you know your luminosity, F. So many watts per square meter. Right? So that is the logic. And my wonderful students, even if you can't parallax something, we're getting better at it. We're getting some good telescopes up to get parallaxes further and further out into the galaxy. But even if you can't parallax, you can still get a color. And what we're going to do on Tuesday and Thursday next week is talk about the relationship between color and luminosity. And matter of fact, I just kind of alluded to that. Betelgeuse is a red star. It's a supergiant. It's really bright. It has a high luminosity. Alpha Centauri C is a red star, but very faint. It's very hard to see. And what does that tell you? It tells you that even though they have the same surface luminosity, Alpha Centauri C is smaller because it's dimmer. And if you can get that, you can figure out all kinds of good stuff. So tonight, or actually by lunchtime tomorrow, if not sooner, there'll be a big reading assignment, and it'll be due Tuesday. And if you want to come up and get an exam printout, come on up. Otherwise, I'll see you on Tuesday next week. You're dismissed.